Hey guys, welcome back to my channel. Today we are going to talk about the first topic in our operating system series, process. By definition, a process is an instance of a computer program that is being executed. Any application, which is nothing but a software program, when a software program is run by the processor, it is called as a process. Let's say our desktops or laptops, right, where you would like to run a web browser, a mail program, a game, a music player, and so forth. All these are basically applications, and all these are basically considered as processes. A typical system may seemingly be running 10 or even hundreds of processes at the same time. Doing so makes the system easy to use, as one never needs to be concerned about whether a CPU is available or not. Only simply run the program, right? But do we have so many CPUs? No, we don't have so many physical CPUs. These days, you might have heard of like octa core, quad core, dual core, right? Now, I think these days we have 16 core CPUs as well, but the number of applications which we want to run simultaneously could be in hundreds, right? So for simplicity in this series, we'll consider that we have just one CPU, okay? We have one processor, and the number of applications we want to run will be more than one. The number of processes we want to run will be more than one. So somehow these processes need to share the CPU, right? This basic technique is called time sharing, which allows users to run as many concurrent processes as they would like. Okay, the potential cost over here is the performance, as you know, each one will run more slowly if the CPU has to be shared. Let's take a quick example over here of a web browser like Google Chrome, which involves several steps from the initial launch to the rendering of web pages. Here is a detailed explanation of how it is executed by the processor. So when you initiate the launch of the Google Chrome, right, the operating system will locate the Chrome's executable file on the disk. This executable file is created by the compiler. Okay, then the operating system will set up the new address space. It will set up the stack and heap process uh, for this particular process. It will then copy the code, the static data, uh, into the memory. Okay, so it will create an address space for this particular process. It will copy the code and the static data. It will set up the heap and the stack memory for this process. So once that is done, the OS will initialize some data structures. It will load the necessary libraries into memory, whichever the Chrome will use. Okay, it will initialize certain routines. Once that is done, it will locate the main thread. Okay, once that main thread is located, the OS will start running this process. Okay, it will create this process and it will start running it. So once the Chrome process is running, the main thread execution will start. The main thread is responsible for initialization of various components of the browser, like the UI, the network stack, and the rendering engine. The network stack, generally you use a HTTP protocol, use the DNS protocol over here. So you need network communication to be set up over here. Okay, the UI is set up. Sometimes you can have multiple threads can be spawned. Okay, and each thread can um, you know work on the rendering engine. It can work on the networking stack. It can work on the JavaScript execution and handling user output input. So these threads will run concurrently on multiple CPU cores, okay, allowing for parallel execution and better utilization of CPU resources. Sometimes they will also, you can create, multiple child processes within a process, which will share, it will not share exactly its address space. It will create an own address space for that child process within its own parent's address space. Then there could be a keyboard and a mouse input which could be given at any time, which will result in an interrupt, and these events are need to be handled, okay, by the interrupt handlers. So this is how the operating system and the processor will launch the process, and it will start executing the process, and it will render the UI and everything. And this is how you are able to use any particular application. Now that we have understood how a process is created, how it is loaded into the memory, and its address space is created, initialized, heap and stack memory is created. Now let's quickly take an example. Before we get into the example, let's talk about the different states of the process. There are three states in a process. Okay, a process can be in one of the three states. It can be in running state. A process is in a running state when it is running on a processor. This means it is executing that particular process instructions. It can be in a ready state. A process is ready to be run, but for some reason the OS has chosen not to run at the given moment. Third state is a blocked state or a waiting state. In this state, a process has performed some kind of operation that makes it not ready to run until some other event takes place. For example, when a process initiates an input-output request to a disk, okay, or it wants to read a file, or it is waiting for some event to occur, until that event is handled, the process will stay in this blocked state. Meanwhile, the processor will execute some other process. Okay, so let's take an example over here. We have two processes. One is process 0 and one is process 1. Both are at t is equal to 1. Let's say our scheduling policy schedules the process 0 to be in running state, and the process 1 is put in the ready queue. Okay, now process at t is equal to 4, process 0 is still running and process 1 isn't still in ready queue. And at t is equal to 4, the process 0 is done. Okay, it's executing its last instruction. So at t is equal to 5, process 0 is done, so it's exited, it's terminated, whatever. And at t is equal to 5, process 1 will be moved to the running state now, from the ready state to running state, and it will run until the process 1 is done, since we don't have any other processes. It's a simple scheduling policy over here. Okay, whichever comes first, they get the CPU unless it is blocked. So let's see the second example, where again at t is equal to 1, we have process 0 in running state and process 1 in ready state. At t is equal to 3, process 0 is in running state, process 1 is in ready state, and process 0 initiates an input-output operation. Okay, it makes a system call, or there is an interrupt that needs to be handled. Okay, so at t is equal to 4, process 0 will move to block state, and process 1 will move to running state from the ready state. Okay, now until t is equal to 7, at t is equal to 7, process 0 moves from block state to ready state. That is because the event that it was waiting for is completed now. Let's say it initiated a system call or an interrupt, and that interrupt handler handled that interrupt, and it has finished executing those instructions, and now it's moved to ready state. Because process 1, it's still in running state, it moves to the ready state. Okay, now at t is equal to 8, process 1 is still running state, it's executing its last instruction. After that, it will get terminated, and process 0 is still in ready state. At t is equal to 9, process 0 will move to running state, and process 1, it's finished, so it's terminated. There is no other process left. So process 0 will keep running now until process 0 is done. Okay, so this is how the context switch from one process to the other process happens when based on the scheduling policy. Okay, and based on these three different states, we can see which process needs to be run, which process is in block queue. Okay, now if there are multiple processes, then these states will have its own queue. It will have its own ready queue, Whichever comes first, that needs to be served first. Queues are first in, first out. Same way, they will have a block queue as well. Whichever comes first, that particular process needs to be handled first. Okay, so that's how these context switch happens over here. So when the context switch happens, right, the processor, the physical processor, has some physical registers. These registers basically store the information about the memory, about the address space, and few more things. Okay, so this information needs to be saved. Okay, that process registers need to be saved, okay, in a structure called as process control block. This process control block basically has all the information about the process, about its memory space, the address space, the kernel stack, the process state, the process ID, if it is a parent process, if it has child process, it will have the context pointer information, it will have all the physical register information which needs to be stored, right? So basically this the storing of the physical registers, right? So this information, it's basically a function is called like context switch function. You write a context switch function, it will call an assembly language code which will save all these registers into a temp variable, okay, for that particular process, and then it will load the other process information into the physical registers. Okay, so it does two jobs. One is save the process which was running, and then it will load the registers of the process that needs to be run. So this is what the context switch function will do, and this is being saved in a data structure, or which is also called as process control block, which has all the process information. Okay, so each process will have this structure. Each process will have the information about the memory address space, the PID, the process ID, and all that information. Okay, do let me know in the comment sections if you have any questions. Please do read about the process, the different states of the process control block registers, and we will also in the next video talk about the different types of scheduling policies, why we need that in more detail. So please do like, share, and subscribe, guys. Thank you.